Okay, we are ready to start, and we are going to start. So it is really with great pleasure that I introduce the first keynote speaker of this conference. And the reason why I tell you that it is with great pleasure that I do so is multifaceted. To start with, Dr. Julian Bommer is not just an academic, someone that carries out state-of-the-art research, but is also very much an active consultant, and therefore is able to bring together the two worlds. So the needs of practical application, the needs of the industry, and the state-of-the-art, the development of research. He is indeed a chartered civil engineer and fellow of the Royal Academy of Engineering, as I said, in addition to the positions that he has held in the past as a full professor at the Imperial College London, and now as a senior research investigator at the Department of Civil and Environmental Engineer, always at the Imperial College of London. Julian has more than 150 publications just on web science alone, with outrageous number of citations, and has carried out field investigations and consulting activities really all over the world. And I'll just cite a few areas: in Algeria, Armenia, California, Colombia, El Salvador, Greece, Italy, Japan, Mozambique, Peru, Turkey. He's been a consultant in many seismic hazard projects, seismic hazard and risk assessment projects. Again, Brazil, South Africa, Spain, US, Abu Dhabi, the Netherlands. But above all, Julian is a really good friend. We've known each other for many years, from my times at Imperial College back in the mid-90s, and he's always been a special friend and a true source of inspiration and guidance to myself. So it is really an infinite honor and pleasure for me to now call Julian Bommer to the stand. Julian, the floor is yours.
Thank you so much, Rui, for those very kind words and the honor of opening this conference with this keynote lecture. The title is clear. I'm going to talk about seismic hazard assessment, both for natural and induced earthquakes, and particularly about Mmin and Mmax. So starting off, my assumption is that we generally now use PSHA, probabilistic seismic hazard analysis, as the basis for defining the input to nearly all seismic design and most seismic risk assessment. The basic elements of PSHA, I'm sure everyone here is familiar with. We first develop a seismic source model, the location and the average annual rate of earthquakes of different magnitudes. We combine these with a model that will predict the ground motion amplitudes at the site of interest from each of these earthquakes. And then inside the seismic source model, we'll define a series of earthquake scenarios. They give us magnitude and distance combinations from which we take the ground motion from the GMPEs. And then we also have to consider the scatter in the GMPEs, and the number of standard deviations we take is epsilon. The annual frequency of exceedance of the resulting level of ground motion, AFE, is simply the product of the frequency of exceeding the given magnitude and the frequency of epsilon, which comes straight from the normal distribution. The frequency of the magnitude simply comes from our recurrence relationships. So that's the basis of PSHA. And when we combine that for all of the possible scenarios, all combinations of magnitude, distance, and epsilon, we end up with the seismic hazard curve, which is our basic output. And it's this part of the recurrence relationship that I want to focus on in this presentation, because it's the recurrence relationship tells us how many earthquakes of different sizes are going to occur. It's basically the motor that drives any hazard assessment. And very simply, if we have higher activity, we'll have higher hazard, and lower activity, lower hazard. And that's very clear. But what's also important is the width of this distribution, where we start considering earthquakes in our distribution and where we end it. These two parameters, Mmin, the minimum magnitude, and Mmax, the maximum. So if we flip this diagram over, so we could put them in the right order, I'm going to talk in the first part of the lecture about tectonic earthquakes. First begin with what is the minimum magnitude, Mmin, and then what is the maximum magnitude, Mmax. And then I'm going to talk about how we have adapted or are adapting this to apply to induced earthquakes, which has become a big issue in the last couple of decades. We'll begin by looking about how Mmax might be considered for induced earthquakes and how similar or otherwise it is to tectonic earthquakes. And then we'll come down and consider whether the minimum magnitude also should be considered to be the same or different. So our starting point is Mmin, minimum magnitude. What is the basis for the minimum magnitude in PSHA? Over the years in practice and in discussions, I've heard many different explanations, that it's the threshold of completeness, it's the smallest magnitude we use in determining recurrence relationships, the minimum magnitude of the GMPEs, or it's chosen just to make the hazard calculations more efficient. None of these actually is correct. Mmax is not, in fact, a seismological parameter. Mmax is an engineering parameter, which is directly related to the seismic fragility of the structure being designed or analyzed. So really, it's the smallest magnitude which could lead to the considered limit state of the structure that's the focus of our hazard assessment. Imagine for a moment that when we did hazard assessment, what we did was generate stochastic earthquake catalogs with hundreds or thousands of events, and for every single earthquake, every magnitude distance combination, that we would select the full exhaustive suite of ground motion time histories and conduct fully nonlinear dynamic analysis. Then what we would end up with, for any given limit state performance of that structure, there would be several scenarios which would stay always below the limit state, that would never contribute to the risk as being defined. Now, of course, that was completely prohibitive, and we could never do that because the calculations would take forever. So we simplify things. The magnitudes and the ground motions get summarized very succinctly in the seismic hazard curve, as I showed a couple of slides ago. And the hazard curve is then combined with the fragility curve, which then summarizes all those dynamic analysis of the structural model. We convolve the two, the hazard with the fragility, and it leads to our final risk estimate. However, because there are scenarios which will not contribute to the risk when we do it the really rigorous way, we have to make sure that those scenarios don't end up inflating the hazard estimate. Because if they do, that will lead to an inflation of the risk. So we try to exclude. It should perhaps be on the basis of ground motion, but for convenience, it's done on magnitude. We exclude high amplitude but non-damaging motions from small earthquakes so that they don't inflate the hazard and don't lead to an overestimation of risk. To illustrate this, why these earthquakes might be excluded, we'll take one right on the boundary of where Mmin is often defined. It usually lies somewhere between 4.5 and 5, and there was an earthquake of magnitude 5 in Nevada, 2008. Very shallow event, just 3 kilometers, and the epicenter was right on the edge of a town called Mogul in Nevada. And there were accelerometers in the town which recorded extremely high accelerations. You can see on that diagram, close to 1G horizontally. This happens to be the house of Professor John Anderson from Nevada. He kindly shared these photos. The station is his house. And you can see what the earthquake did. It knocked books off shelves, it knocked paintings off walls, it caused one small crack in plaster, but it didn't cause any damage, despite the level of acceleration. And in their paper on the earthquake, Professor Anderson and colleagues concluded several hundred homes constructed primarily since the 1980s, and probably therefore code compliant, were exposed to shaking in excess of 0.5 G. Very few sustained damage more significance than cracked plaster. The reason is, despite those high accelerations, that what we've got is duration of very short motion and consequently with very little energy. And that's what Mmin is really trying to take care of, is not to pump up our hazard estimates with these very short-lived, low duration, low energy events, which wouldn't actually be contributing to the risk. In the paper I published with Helen Crowley, we offered the following definition, that Mmin is the lower limit of integration over earthquake magnitudes, such that using a smaller value may result in higher estimates of seismic hazard, but would not alterate the estimated risk exposure under consideration. And if we accept that definition, we see that hazard is always and inextricably linked to risk, something Helen will talk more about in her joiner lecture on Thursday afternoon. Okay, now we're going to jump up to Mmax for tectonic earthquakes, the other end of this distribution we're integrating over. And what is Mmax in PSHA? Mmax is essentially the largest earthquake that could occur in any given seismic source in our SSC model, our seismic source model. And Mmax is a very good example of what we call epistemic uncertainty. It's a number that cannot be known with certainty. It's a number that has to be estimated from uncertain data and involves extrapolation. And therefore, it should appear in our logic trees, and the node for Mmax should capture the center, body, and range of possible values, to use the PSHA terminology. This is an illustration of what we mean by center, body, and range, that for any given parameter, in this case Mmax, we'll have a frequency distribution. That's not going to show. The center of the distribution will be the peak of the distribution. The shape of it is the body, and the upper and lower limits are the range. However, we're good at building these distributions for most parameters that we put into PSHA, but there's a tendency, and I think it might be related to the fact that it contains the word maximum, that when we're looking at Mmax, there's a tendency to focus only on the upper end of the distribution and only answer the question, how big could the biggest earthquake be? But if we're trying to capture a distribution which captures the center, body, and range, we also have to answer the question, how small could Mmax be? How small could the largest earthquake end up being? Now, if we have fault sources, if our earthquakes are all going to happen on mapped known geological faults, then estimating Mmax is relatively straightforward because we can use the fault dimensions and empirical relationships. But even there, we have to make decisions. There are many empirical relationships between the rupture dimensions and magnitude, so we might choose the most conservative of those. We also have to make a decision about, will the entire length of the fault rupture? That's quite a rare occurrence. It's much more likely that only some proportion of the fault will rupture, and that also be considered. It's also been proposed that we shouldn't be using the median value from these empirical relationships, but rather should be using 1 or even 2 standard deviations above the median. And all of these proposals are absolutely fine for defining the upper end of the Mmax distribution, but they won't give us the full distribution that we need to capture the full epistemic uncertainty, in my view. Now, a slight caveat as well on all of this is that in general, one would think that taking high Mmax values is conservative. Higher Mmax, bigger earthquakes, we're going to get higher hazard. There is an exception to that, and it's when we're looking at fault sources, because fault sources don't actually generally obey the standard Gutenberg-Richter recurrence relationship, but the characteristic relationship, where the largest earthquakes occur as quasi-periodic events, which are identified from geological data rather than from the seismicity data. And I'm going to show you an example of finding characteristic earthquakes on a fault, and it was for the Panama Canal project that Rui mentioned. So the extensive geological investigations were carried out for the expansion of the Panama Canal, and these identified several faults previously unknown or unrecognized that turned out to have high levels of activity. The most important is this one here, the Pedro Miguel Fault, which runs very close to the new locks and actually goes right through one of the embankments for the overspill data basin. And that fault was investigated in great detail. There was extensive trenching along that fault. The fault runs approximately across the site like this. And what these investigations revealed was that there was clear evidence of recent displacement on that fault. And at one point, there were a lot of people, and including a lot of geologists in the field, looking at these trenches and just trying to interpret what was being looked at. And there was clear evidence that over a period of approximately 5,000 years, a total displacement of 5 meters had occurred. And there were two schools of thought. One was this had all occurred in one very large earthquake. So that would give us, if we work back from this empirical relationship, that a single M7.7 earthquake occurs every 5,000 years. An alternative interpretation was that actually that displacement occurred through a sequence of events, more like magnitude 7 earthquakes occurring once every 1,000 years. So the question that then arises, which of these is going to give us the higher hazard? Instinct would tell us that the higher magnitude will give us higher hazard, but this actually turns out not to be the case. If we come back to this equation, that the annual frequency of exceedance is the product of Fm and the frequency of the magnitude and the frequency of exceeding epsilon, we can rewrite this by taking reciprocals, that the return period of the ground motion is the recurrence interval of the earthquake divided by the frequency of exceeding epsilon. And if we have a target return period, for example, 10,000 years, which is appropriate for such a critical structure, then for each of these magnitudes, we know its recurrence relationship from what we just saw. We can calculate what epsilon is needed to give you that resulting return period. And when we get these combinations of magnitude and epsilon, they both have the same distance of about 1 kilometer from the new locks, and plot the resulting response spectra, what you see is that the smaller earthquake, by virtue of occurring more often, actually gives higher hazard. So it's not always the case that larger magnitude gives us larger hazard. And I want to go, it's very often the case that we can't have fault sources at all. We can't associate all our earthquakes with known geological faults, so we have to use area zones of distributed seismicity. And then it becomes really a challenge to define what the maximum magnitude is, because there's no structure we can measure. Having said that, there will be cases where we'll end up with a combination of the two. We'll have fault zones embedded within area source zones. And in these cases, the Mmax that we are assigned to the floating earthquakes, the distributed seismicity in each source, should be capped at a value lower than the magnitude that occurs on those faults. Because if the faults are there and modeled, they should be localizing structures for the largest events. And only smaller events than that should occur around them. Alternatively, sometimes the faults will not be included explicitly as separate sources, but people will say we'll use those fault dimensions to determine Mmax for the entire source. And you could argue that that's extremely conservative because that fault's in one location, and yet you're saying that an earthquake that would require a structure of that size could occur anywhere inside that seismic source zone. Now, it turns out in practice that very often we just end up putting quite high values of Mmax on our logic trees, and people spend not too much time on it because we have this idea that that hazard is actually rather insensitive to the value of Mmax when we're dealing with area sources. And this is true when our logic tree only has large values of maximum magnitude, as you can see in this case. It's not always true, and the problem is that we keep setting up logic trees like this because we've convinced ourselves that the hazard's insensitive. Now, the reason it's insensitive to large values of magnitude is simple. It's because as you get to these very large magnitudes, especially if we have a taper, the recurrence rates of these earthquakes drops off very quickly, and they don't contribute very much to the hazard. At the same time, as we go to larger magnitudes, our ground motions don't keep increasing linearly, they begin to saturate. So we get lower rates of occurrence of the earthquakes, which is not offset by greater levels of ground motion because of this saturation effect. And on top of that, these less frequent earthquakes sample less values of the standard deviation, and we have smaller epsilons. So all in all, we end up not contributing very much to the hazard with these large Mmax values. However, in stable regions, we often use what's called the Bayesian approach. And what this is based on is that people studied all the stable continental regions of the world. They built a catalog of the largest earthquake in all these regions and built global distributions of Mmax values in stable continental regions. This becomes our prior. Then what we do is construct for our target region a likelihood function based on the local earthquake catalog. It starts abruptly at the largest magnitude that's been observed, because obviously Mmax cannot be smaller than the biggest earthquake you've seen. And the sharpness of that peak on that distribution depends on how many earthquakes you've had that are a little bit smaller, maybe within half a unit smaller than your largest earthquake. This is a case where there have been a few events close to 5.2 or 5.3 in this case, and you get a rather peaked distribution. You use that likelihood function to update the prior, and you get your posterior distribution, which can then be resampled as discrete branches for your logic tree. Now, in this case, it's very different. We're not simply putting very large values. We have a distribution which goes right down to the lower end of the distribution is actually controlled by the largest observed earthquake. And when we do that, we end up with a very broad distribution of Mmax values. And what we see is now the hazard is very sensitive. This idea that hazard is insensitive to Mmax is only true when all your Mmax values are big. When you have a proper full distribution, Mmax matters quite a lot. So that's something to keep in mind. And then when we're doing this, we should think carefully about these very large values we put on the upper end of the distribution, like the 7.9s. If you put a 7.9 into any of the empirical relationships for scaling, what we see is we've got rupture dimensions measured in hundreds of kilometers. And if we're saying that we have that kind of Mmax inside our source zones, we're saying that there are geological faults in those zones capable of producing such an earthquake. Now, to explain how we might get insight onto that, I'm going to take a small detour and talk about virtual fault ruptures. These are faults that don't really exist, but which we create for PSHA. In PSHA, when we integrate across a source zone, we effectively need to discretize the source zone either into arcs or points, and then we measure the distance from the site to those points, and in effect, we're measuring epicentral or hypercentral distance. Okay, we measure distance from a point. However, our ground motion prediction equations, our GMPEs, use distances which are measured relative to an extended fault rupture. An example, we go back to the Tabas earthquake in Iran, 7.4. It recorded here at the Tabas station, very, very strong ground motions. That's the epicentral location. It was a very shallow dipping thrust fault you can see some of the surface expression there, dipping to the northeast. That blue rectangle is approximate projection of the fault rupture up to the surface. So for that recording, the epicentral distance was 60 kilometers, but the Joy-Nabor, the fault-based distance, is only 4 kilometers, which is a much more realistic measure of how close we are to the energy release. However, if we take an equation based on RJB, on the Joy-Nabor distance, and combine it with calculations based on epicentral distance, because the epicentral distance is always greater than or equal to RJB, we're going to underestimate significantly the hazard. So the rigorous solution to this, there are a few ways out of this, but the rigorous solution is for every earthquake that you generate inside the source model, generate artificial or virtual fault ruptures who have dimensions related to the magnitude, which initiate at that point and extend. The orientation can be controlled to reflect the structural fabric, the geological fabric, and then calculate correctly the distance. You can see here an example from the work published by the GEM team. The hazard curve with the circles is using point source representations, and the other two curves are using different degrees, different types of virtual fault rupture, and you can see it puts the hazard back up to where it should be. So these virtual faults are a really important part of getting our hazard calculations correct for area source zones. The thing is that most good seismic code, PSHA codes do this. They generate these virtual fault ruptures, but they do it inside a subroutine. It just happens behind the scenes in a black box, generates the fault ruptures, get the distance, it comes out, and you carry on. But it's actually really worthwhile taking a look in midway, stopping and visualizing what your virtual fault ruptures look like. This is, I've anonymized this, but this is from a real and recent project. So that's a source zone, which is fairly large, and every one of those gray lines is one of the virtual fault ruptures. Every single one initiates inside the source zone and then has rupture dimensions consistent with Mmax. Some of them barely stay inside the zone. You have to have what we call leaky boundaries to accommodate these faults. But every single one of those lines, well, the statement we'd make is that every virtual fault rupture should correspond to a physically possible but as yet unidentified geological fault. So you have to look at a map like that and say, do we really believe that there are faults there, dimensions of 300 kilometers plus, which have gone undetected but could rupture in future earthquakes? I know it happens. The Bhuj earthquake in India was an example of a previously unknown earthquake generating a large, unknown fault generating a large earthquake, but it's very rare. And if you produce a map like this, and it makes you doubt, then perhaps we need to rethink some of the upper end values of Mmax that we're using. So what I would argue in summary is that for natural earthquakes, the distribution is not sufficiently wide, it doesn't come down low enough, and the upper end may push a little too far. Excuse me for a second. So, I'm now going to move on to induced earthquakes, because what we've learned over the decades about tectonic earthquakes is being moved into the application and adaptation to induced earthquakes. Firstly, what are induced earthquakes? Basically, earthquakes related to pressure change or stress changes due to fluid injection or extraction. There are other mechanisms like mining, but that's what I'm going to mostly focus on. Induced seismicity is important because it poses a major threat to energy-related technologies, including deep wastewater proposal, shale fracking, and enhanced geothermal systems, so anywhere which involves high pressure injection into the ground, and also underground gas storage, which is very important, and particularly as we go forward trying to combat climate change, carbon sequestration, which is looking to store underground volumes of gas that have never been stored previously. So getting to grips with induced seismicity is really important for our energy security. I have to then talk about the difference in what we call induced and triggered earthquakes. An induced earthquake are small, relatively small events which occur directly due to stress increases caused by the operations. The energy released by an induced earthquake is the energy provided input by the industrial operation that caused it. In contrast, a triggered earthquake is a tectonic earthquake initiated by fluid-induced pressure changes leading to runaway rupture on geological faults. In that case, when you have a triggered earthquake, the energy released by the earthquake is actually stored elastic strain energy that is already in the crust. An example, which I'm going to talk about more later, the Castor offshore gas storage, about 20 kilometers off the shore of northeast Spain. You can see the recurrence relationships here. There's two phases, one during the injection and one after injection. It's probably slightly oversimplification, but you can see very different characteristics. A very high B value during injection, relatively low activity. Those we would classify as induced earthquakes. The events which occurred subsequently, which follow a more closer to a B value of 1 and achieved higher magnitudes, these would be triggered tectonic events. Just on this terminology, it gets very confused because we use induced as the umbrella word as well. So what we've recently proposed is that we would talk about driven earthquakes rather than induced, because induced is always going to be used as the umbrella term. So driven and triggered earthquakes. So Mmax for induced seismicity. There was a USGS workshop in 2014 where they brought a lot of people together to discuss how they might set up calculations to include for the first time PSHA inside induced seismicity inside the national hazard mapping for the US. And what that workshop concluded, it wasn't exactly what ended up being done, but what the workshop concluded was participants felt that the USGS induced seismicity model should consider the possibility of triggering large regional earthquakes and should consider the same Mmax distribution as for natural seismicity. And this has gone, a lot of people have adopted that view. If you look at any given situation, however, we need to keep that distinction between induced and triggered seismicity. This is a logic tree that's been set up for Mmax in the gas field of Groningen in the Netherlands. And you can see the first node of the logic tree is to distinguish between purely induced earthquakes and the possibility of actually triggering tectonic earthquakes. And again, if we want the full distribution, we need to have those two options treated separately rather than say only going to have large triggered earthquakes. So Mmax for triggered earthquakes. For fluid injections to trigger large tectonic earthquakes, we need a number of factors. First, we need to have faults which are large, favorably oriented, and already critically stressed. A mechanism which will transfer the pressure stress and change from the injections to wherever the fault is located, which may be at greater depth. And then we need large fault ruptures that initiate at shallow depth and propagate primarily downwards. And that's actually a very rare situation. Hypercenters are generally found to be in the lower 2/3 of a fault rupture, or even the bottom half more commonly. So it is quite rare to find earthquakes, large magnitude earthquakes, which start shallow and propagate only downwards. In fact, 40 years ago, Daz and Schultz published a paper where they explained, in terms of increasing gradients of confining stress and frictional strength, why downward propagating ruptures causing large earthquakes are very exceptional or are unexpected. They do occur. They occur in a few geological regions of the world, but they also occur exceptionally in certain events, like in the Ridgecrest earthquake in California, where the magnitude 7 earthquake initiated at 4 kilometers depth, but it's believed that this was caused by stress transfer from a deeper magnitude 6.44 shock. And in his paper on that, Lomax says the shallow M7.1 nucleation, for which spontaneous rupture growth into a large earthquake is not expected, may have required this incitation by the M6.4 event. So I'm not declaring that shallow events, large magnitude events cannot initiate at shallow depth, but it is very rare and will only occur under exceptional circumstances. Consequently, we could conclude that Mmax for triggered earthquakes should be less than or equal to Mmax for tectonic earthquakes. It's not necessarily always appropriate to simply adopt the Mmaxes we're using for tectonic seismicity. Now, what about Mmax for the induced, or as we're calling it, driven seismicity? Let's first look at the lower bound. In cases where the injection or extraction has been in operation for some time, I propose that the lower bound of Mmax should actually be the largest observed earthquake. So if I go back to that distribution for Groningen, that's now recast as a histogram there, combining the induced and triggered events with their weights. We can transform that into a continuous distribution. And what we can note is that the largest earthquake that's happened in Groningen actually had a magnitude 3.5, which is assigned 0 weight on the Mmax distribution. Now, Mmax is an epistemic uncertainty in general, and it can never be tested for natural earthquakes. But in induced earthquakes, it can. We do have the possibility that Mmax will sometimes be tested. If you fully produce a formation, or for example, if you fully extract all the gas from a formation, such as if the Groningen project had continued, if when it's all over, an equilibrium has been restored, the largest earthquake was smaller than the lower bound of your Mmax distribution, the Mmax distribution was wrong. Okay? If we have a full set of observations of what's actually happened, one of our sort of rules of thumb for epistemic uncertainty is that it should lie within what actually, your distribution should cover what actually happened. So I would say, just like we do quite comfortably for stable tectonic regions using that Bayesian method, the Mmax distribution for driven seismicity should begin at the largest observed earthquake. What about the upper bound? Well, the upper bound is actually not for driven, this is not for induced, is not driven by tectonic stresses, but rather by controlling factors that are primarily operational. Things that control the pressure changes or stress changes within the crust, such as the volume of fluid that's been injected. And this famous diagram from Art Magar, which proposes an upper bound, which induced events should not exceed, which gives you the upper bound magnitude in terms of the total injected volume. There's all those cases up at the top end there are massive wastewater injection projects in the US. So we have this as a possibly absolute upper bound on Mmax for our driven seismicity. But there are other factors. When we're injecting fluids, we often will deploy traffic light schemes. And the idea of a traffic light scheme is you set up seismometers, you observe in real time any seismicity that happens. If the magnitude stay below a certain level, it's your green, you carry on without any interruption. If the magnitude increases, you go into yellow and you start to modify the operations, reduce pressures, reduce flow rates, so that you can avoid going up to the highest magnitudes. And if you hit red, then you're generally required to stop, possibly flow back and reassess whether the project can continue. Now, what's been seen in practice is that traffic lights don't work perfectly. And several people, myself included, over the years, have said we can't really trust them, because this is what we want to happen in theory, is that as soon as we hit a red light, we take the drastic decision to stop the operations, we start to reduce the pressures, and we hope that the seismicity will immediately start to drop off. In some circumstances, it's not always the case, but in some circumstances what we see is we stop the injections and the seismicity continues. Not only does it continues to increase, and we get these so-called trailing events. And these have made people not want to use traffic lights or not rely on them because they don't stop these trailing events happening. However, we now have a good database of what these trailing event magnitude jumps look like. And we can see the statistics. They're still the exception rather than the rule. And generally, they won't ever exceed about magnitude 1.5 at largest. And we also have, not for traffic lights, but we have evidence of what's the largest magnitude jump in induced seismic sequence from massive operations injections. So what we could think about is if we do have any kind of control scheme, like a traffic light scheme, then we could say, not necessarily the absolute upper value of Mmax on our driven earthquakes, but a highly weighted value could be the red light magnitude plus whatever delta M, whatever magnitude jump that we're comfortable to live with based on the statistics from these databases that are now being compiled. Okay, so that's Mmax for induced earthquakes. We're going to finish with Mmin for induced earthquakes. Remember that Mmin is the smallest magnitude which can cause damage to the structure of interest. And it's often argued that Mmin should be smaller for induced earthquakes, and this is argued because of their shallow depth. You have a shorter travel path, so the motions are going to experience less attenuation, and you're going to get higher motion at the epicenter. Okay. That ignores the fact that if we have lower shallow depths, something we call the stress parameter, which is how intense the radiation is from our earthquakes, is also going to be lower, and that will tend to lower the ground motions. Moreover, when we look at tectonic earthquakes, they will tend to propagate the waves mostly through high VS and therefore high Q material, which means very low attenuation, whereas the induced earthquakes would be traveling and the waves will be traveling mostly through softer, more absorbent material with lower Q and experiencing more attenuation. So we need to consider these two factors together. And it's been verified to some extent by data, intensity data, did you feel it data that was collected by Susan Huff. She looked at tectonic and induced earthquakes in Central and Eastern United States, and she looked at the intensity patterns. And she saw indeed that for the induced earthquakes, the intensity drops off is lower at distance because of the higher attenuation, and probably because of the lower stress parameters near the epicenter. The effect of shallow depth and lower stress parameter roughly cancel each other out, and you get very similar levels of intensity whether the earthquakes are induced or tectonic. And this was confirmed in a paper by Gail Atkinson and others, published in 2018, they concluded that for moderate earthquakes in the range we're interested in, 4 to 5.5, induced and natural events have similar intensities and thus equivalent damage potential at distances close to the epicenter. And because of that, models now take into account this stress parameter effect, the interaction of stress, magnitude, and depth. Because of this, we could conclude that Mmin should be the same for induced and natural seismicity. There doesn't seem to be a compelling reason that we should be using smaller Mmin values for induced earthquakes. Now, when I propose that, people will come back and say, but some small magnitude shallow earthquakes generate very high PGAs. Yes, even some natural earthquakes do, like the Mogul earthquake I showed you. But they do. There's a geothermal project in El Salvador. This is one of the first times a traffic light was ever used. During one of the inter-injection periods, there was a trailing event, magnitude 4.4 earthquake. We set up a lot of accelerographs in the affected area to monitor any ground motions, and we recorded very high accelerations, 0.8 G. And yet, if you look at the very, very vulnerable housing in the villages where that instrument was located, there was no damage. Why? Again, because look at the accelerogram. Its total duration of strong shaking is not even half a second. So yes, you have high amplitude, but it's very short-lived, very high frequency, and very low energy. So yes, some earthquakes do small earthquakes do produce high PGAs. If they didn't, we would never have actually needed Mmin in the first place. That is exactly why Mmin was introduced, was because some small earthquakes produce high amplitude, short duration, non-damaging motions. Another objection is that some small magnitude induced earthquakes have caused damage. And there I would challenge those claims. The one that I get quoted most often is the Basel deep heat mining project, an enhanced geothermal project in Switzerland. It was a very big project in downtown Basel, designed to provide renewable electricity to 10,000 homes, plus district heating to almost 3,000 homes, injecting at about 4 kilometers depth into very hard and hot rock. What happened was in December 2006, not long after they began, they triggered a magnitude 2.6 earthquake. That triggered the red light. They shut down immediately the injections, and then a few hours later there was a trailing event of magnitude 3.4 ml, 3.2 moment magnitude. They had a network installed by the Swiss Seismological Service. They recorded maximum PGA of 0.1 G. So a magnitude 3.2 earthquake, 0.1 G doesn't sound very onerous. But there was actually, they paid out $9 million of insurance for damage claims for buildings in the city of Basel. And this is why it's often reported as a damaging earthquake. But we have to look a bit deeper. What happened was, these were all settled without on-site inspection. The Basel project was actually owned and initiated by the city of Basel, and they announced on public radio that if you lived in Basel, there would be no legal disputes and there'd be no political controversies. If you submitted a claim up to a certain value, it would be honored. And $9 million of damage claims were paid out. In the next slide, I'm going to show you. I asked for images of the worst cases of damage that occurred. And here they are, right? Okay, I could help you because we haven't got that much time. If you look closely, there are some cracks. Most of you could find cracks like that in your homes if they're more than 5 years old now. Okay, my favorite is this one, a split in the timber column, which has also been attributed as earthquake damage. Okay, so this is a case where insurance damage claims and damage are not necessarily the same thing at all. And it's interesting to note that there was another another enhanced geothermal project in another part of Switzerland about 6.5 years later, which produced very similar seismicity. So a place called St. Gallen on the eastern side produced actually a slightly larger earthquake in terms of moment magnitude was 3.4. It was slightly shallower, and you can see here the red is the average PGV levels from St. Gallen, the black is from Basel, even produced slightly higher levels of ground motion. So a similar event, but slightly stronger in St. Gallen than in Basel, and yet there were not a single report of damage or claims for damage in the St. Gallen case, which really does raise strong questions about what happened in Basel. Nonetheless, the Basel project was first suspended because of the earthquakes, and then the city of Basel commissioned a risk study on the basis of which they closed the project down forever. And the reason that happened was because the first thing that the risk study did was on the basis of geophysical modeling conclude what was the largest earthquake that might occur if the project continues, and they concluded M4.5. That maybe is reasonable, but the risk estimates that they obtained were based on extrapolation from using the insurance data rather than any observations of damage. And that gave such high economic losses from a magnitude 4.5 earthquake that the city considered this untenable and refused to allow the project to restart. Even though the report said, even it is not proven, and as far as we know, no attempt was done in that sense, the damages were for sure caused by the earthquake, we consider these values as direct consequences of the 2006 earthquake. So we're never going to get out of this hole with induced seismicity until we properly quantify risk. Not just hazard, but risk. What is the real physical impact on buildings of these small induced earthquakes, which seems not to be particularly onerous. Okay, so that's the diagram I've worked and talked you through. I'm now going to give you my conclusions, although I'm not going to finish exactly on this slide. I've got a couple to follow, but my conclusions are that the way this is often treated is that we treat Mmax as being the same for induced and tectonic earthquakes, and Mmin as being lower for induced earthquakes than tectonic earthquakes. This gives induced earthquakes a very bad press. It doesn't give them a chance. It makes induced earthquakes look terrible. I believe that both those signs, those mathematical signs, reflect misconceptions. If we accept that there are several reasons why Mmax for induced seismicity should be smaller than Mmax for tectonic earthquakes, this should be replaced this equal times by less than or equal to, and possibly significant less than. Also noting, as I was in the first half of the lecture, that Mmax estimates for tectonic earthquakes are generally biased high. In terms of Mmin, I haven't seen compelling evidence to support the idea that Mmin should be any different for the two types of seismicity, so we should replace that red sign with an equal sign and adopt the same values for both types of seismicity. And in finishing, I have a few slides of why this matters. During this week, we're going to be talking about large magnitude earthquakes. We heard reference this morning to major earthquakes which have occurred in Italy, Turkey, Syria, Morocco. That's why all of us became engaged in this subject, right? To stop those disasters. But earthquake engineering has a role to play here in making common sense prevail in terms of managing induced seismicity as well. And as I said a few slides ago, there is a real threat to energy technologies because of not getting this right. And many projects, Basel being one of them, have been disrupted or even shut down because, in the first place, of exaggeration of the impact of small magnitude induced earthquakes. In other words, we're underestimating Mmin. We're starting to believe that very small earthquakes, even though what people might feel, are also damaging. And often they're not, as I think I've tried to show you. The final justification for shutting the projects down, however, is usually based on what could happen if the operations continue. In other words, the impact of an Mmax scenario. And I'm going to go back, as I said I would, to the Castor gas project in Spain. What it did is that there was a depleted oil reservoir 20 kilometers offshore, and they decided to use that for gas storage. Spain is short of gas storage, so it's a very clever idea. When they started to inject the gas, some seismicity began, and there were a series of earthquakes, and after one of the shut-ins, the largest earthquake of the sequence occurred. It was 4.2. That's the seismicity. It's about all of it 20 kilometers offshore. The Spanish Seismological Service assessed the intensity on land. The highest value of intensity is 3 on the EMS 98 scale. The EMS 98 scale 3 is defined as weak motion. The earthquake is felt indoors by a few, no damage. In other words, these earthquakes had absolutely no impact on land. But still, the project got shut down. And part of the reason it got shut down was because not long after the earthquake occurred, a report was issued by some US academics. It was never published in a journal. It was just a private report where they attributed the earthquakes to this Amposta fault, which you can see mapped there, a fairly large structure. They concluded that continued gas injections could trigger a magnitude 6.8 earthquake on that fault. Now, 6.8, even at 20 kilometers from the shore, could start to have some serious consequences. You can see why the concern was raised. However, the Amposta fault doesn't look like that. The original map, mapping in a PhD thesis, which drew that very large orange line here, is based on very limited and incorrectly joined geophysical data. It's been reassessed to have the trace that you can see there on the right-hand side of that map, the much smaller green line. But moreover, it's probably not a tectonic fault at all. It's widely believed to be a listric fault, which becomes horizontal at about 3 kilometers depth, and it may even be associated with salt tectonics rather than co-seismic tectonic deformation. Now, a lot of papers got published in journals, not by the authors of that report, but by many other seismologists and geophysicists in various journals, and some of those, their evolution of the ideas of what happened, some of those even ended up with some quite heated debates between the authors of those reports. But the one thing they all agreed on is that the earthquake did not happen on the Amposta fault. It occurred much deeper on a much smaller fault. Now, why is this significant? Not only because the project got shut down, but it went to court. Now, we're in Italy, and I'm sure most of you will remember the trial of the L'Aquila 7, who were found initially guilty of not predicting an earthquake. I'm sure you remember that scandal and the happy news that most of them were subsequently committed. Far fewer of you probably are aware that the leaders of the Castor, the two gentlemen who set up the Castor project, were also put on trial, in this case for an earthquake that they might have triggered had the project continued. Okay? And had they been found guilty, they'd have gone to prison for 7 years for causing an earthquake on a fault that probably doesn't exist and which could not have occurred. So when we start throwing these numbers around about what our maximum magnitudes and minimum magnitudes are, we need to be careful because these things have consequences. And I'm going to finish with an example where the consequences have been devastating, and it's the Groningen gas field in the Netherlands. When it was discovered, the 7th largest gas reserve in the world, it's right there, shaded there in the north of the Netherlands. Discovered in '59, production began in '63, and induced seismicity in 1991. You can see here on the upper plot, you have the histogram of gas production per year, and you can see the fairly good correlation with the number of earthquakes. And look at the magnitudes. Okay, the biggest earthquake, as I showed you before, is 3.6 on the ML scale, and you can see that mostly these are events from 1.8 and higher. The biggest event occurred in 2012 in August. It had a 3.5 moment magnitude and began a great crisis, which led eventually to the field being shut down, which is partly interesting because 6 years earlier, there'd been an earthquake of almost exactly the same size, fractionally smaller, 3.4 moment magnitude, which was just accepted as a routine event for which 300 claims were settled and life continued as normal. Now, to very briefly introduce it, the gas reservoir in Groningen is about 3 kilometers depth in a thin sandstone layer. That sandstone layer is offset by very, very old geological faults. And what's happening is, as the gas is extracted and the reservoir is compacted, where there are these fault offsets, the faults are being reactivated and beginning to generate these small earthquakes. All the earthquakes to date have occurred inside the reservoir. There's no evidence for them exiting the reservoir, and it only has a thickness of about 300 meters. So if you take a fault aspect ratio of about 3.5, length to width, which is about as ribbon-like as we could make a fault, then if you rupture the full width, then you get a magnitude close to 4 if you use certain scaling relationships. So that would appear to be physically constrained on the largest earthquake that would occur if things are carried on as they have been to date. Now, while I explain that the field has been shut down, and with a lot of gas still in the ground, I have to just qualify some of the things that have been said. One of the reasons it's been justified, if you think just shutting down a major resource because of a magnitude 3.5 earthquake, well, one of the reasons that's been given for that is that these earthquakes produce exceptionally high levels of ground motion because they're shallow and because the region is covered with soft soil deposits, clays, and peats. In fact, we don't need to speculate about this because there are very, very dense networks of recordings, and the biggest PGA that's been recorded is 0.1 G, and the biggest PGV is 3.5 centimeters per second. These are not onerous levels of ground motion. If we compare them with ground motions of other parts of the world, if I take Gail Atkinson's equation based on California data but derived for application to induced seismicity, these are residuals of PGA and PGV, so residual is observed minus predicted, so negative is over prediction. Her model tells us the motion should be twice as high as what we're recording in Groningen. Moreover, the Groningen motions, as you can see from those red lines, are attenuating more rapidly with distance than tectonic earthquakes. And on top of that, even when we do get these motions, which are on the order of 0.1 G, they're associated with tiny durations. That's the strongest record in terms of PGA, and it has a 5 to 75% iris intensity duration of less than half a second. So are the levels of motion exceptional? Yes, they're exceptionally weak, if anything. But again, we see a picture which tells us there's a lot of damage. These are damage claims in numbers on the vertical axis against the date. And the red lines are earthquakes that have occurred of different magnitude. Now, if everything was operating properly, this would be a step function. You'd have an earthquake, you'd have a jump up in claims, things would settle down, you get another earthquake, and we'd see a step function. You don't see a very strong correlation between the red lines and the gradient and amplitude of this curve. It begins with the Hausinger earthquake. There were previous events, but we're starting here. You see it was all flat. The Hausinger earthquake comes along. You get exactly the step function predicted. You get a number of claims, and it starts to level out in the months afterwards. But then a few months later, the regulator published a report which speculated about how much bigger the earthquakes could get and raised a lot of other questions. And this report became very public, and it changed the way the earthquakes were viewed completely. In my view, it manufactured a crisis. And you can see that then things started to go up much more significantly. At one point, the Dutch government said that repaying damage is not enough, that if someone's house has been affected by it, you also have to improve the house, which meant putting solar panels on the roof. When that policy was introduced, we see a very sharp increase in the gradient of the number of claims. After a while, the field operator said, this is clearly not fair. The government agreed and removed that measure, and bang, the gradient of claim rates went back to what it had been before that. And now, as you can see in recent years, when there's a new agency not only handling but promoting these damage claims, it's going off the scale. And people are claiming for damage from a 3.5 earthquake at 30 or 40 kilometers from the epicenter. They need some earthquake engineering. So, as I said, on the 1st of October last year, the field was closed by the Dutch government. 25% of the gas is still in the ground. Groningen gas is 25% nitrogen, about 15% nitrogen. It's what we call low calorific gas. So now the gas is being imported to replace it. I'll let you work out for yourselves where it's coming from and who's benefiting from that. But it's being brought into the Netherlands, mixed with nitrogen to make it look like Groningen gas, because that's what everything in the Netherlands is calibrated for. So people who wanted the Groningen field to be shut down because they don't like fossil fuels have helped to contribute to a doubling of the carbon footprint of gas consumption in the Netherlands, and all because of an earthquake magnitude 3.5. And the biggest loser is the Dutch state. This was a good resource for the companies that own it, which is Shell and ExxonMobil, but the biggest shareholder is the Dutch state, who got 90% of the income and made to date 1 trillion euros direct income from the field. The real reason it got closed down was not only exaggeration of what's actually happened, but as I said, speculation of what might happen, which is why we have to be really careful when we start throwing Mmax values out. And what the regulator said was, as long as people in Groningen run a higher risk of dying due to collapse of houses as a result of a major earthquake, phasing out gas production will remain necessary for the safety. So in other words, what's going to happen very often is, even though Mmax is part of a distribution of where we truncate the upper end of our integration in PSHA calculations, it's often going to be treated as a prediction of a scenario value. And that will always cause difficulties, especially in a case like this, when there are compelling physical reasons why the kind of events that are being spoken about couldn't physically occur. So I know this week we're going to talk about much bigger magnitude earthquakes and real earthquake engineering of protecting large structures from large magnitude events, but there is a real need for a risk perspective and an earthquake engineering perspective to help manage induced seismicity, which is potentially posing a major threat to energy technologies, including some that are very important and what we would call green technologies like geothermal systems and carbon capture. And I hope some of that has been interesting for you, and thank you for your attention.